Okay, so today we're going to look at section 6.1. We are doing operations on functions. You can see our learning target there. We're going to add, subtract, multiply, and divide functions. And then the new operation today is the composition of functions. So we will be able to add, subtract, multiply, divide, and compose functions. All right, so I'm going to give two functions, and we're going to do different operations on them. So we're going to let f of x equal x plus 2 for now. And we'll let g of x equal 3x minus 1. So we're going to do some different operations with those. We're going to start off with first adding. So here's the notation that you might see. There's a couple things you might see. You may be told f of x plus g of x. That one should be fairly straightforward, but that's not the notation that you'll probably see quite as often out of the book as this. They might just skip the x for a moment and say f plus g, and then of x. They just put it at the end. So we're doing, really means the same thing. Both of those notations mean to add together f of x and g of x. So take your f of x, which is x plus 2, and we'll add to that g of x, which is 3x minus 1. And this one is just as easy as adding together like terms. So when we add them together, what do we get? 4x plus 1 is correct. Let me go over here, actually. Let's do subtraction. So you might see it as f minus g of x, or you may see f of x minus g of x. That's the notation I prefer, but the first one, the top one, is what our book tends to use. So either way, we have to start with f of x, which is our x plus 2, and we are just going to subtract away g of x, which is our 3x minus 1, which gives us what? Negative 2x plus 3. What's subtraction? Remember, so x minus 3x is the negative 2x, but then you have 2 minus a negative 1. So minus and negative functions as plus. So 2 plus 1 gives us the 3. And then we can do multiplication. This is how the textbook will probably write it, f times g of x. Could also say f of x times g of x. So listed f of x first, times g of x. And then to multiply that, we can use our FOIL or distributive property. 6x squared minus x plus 6x minus 2. When you do all of your distributing, combine your like terms together. I have 6x squared plus 5x minus 2. So my FOIL was this, x times 3x, x times negative 1. Oh, sorry, I did make a mistake. Thank you for pointing that out. So that should have been a 3, not a 6. I saw my 2, I guess. That was supposed to be a 3. Thank you for that. 3x squared minus x plus 6x minus 2. So if I rewrote that, let me erase. 3x squared plus 5x minus 2. Okay, And then division, they're probably going to write it in fraction form. So f over g of x means the same thing as f of x over g of x. So f of x is going to go in the numerator. G of x is 3, goes in the denominator. Can that fraction be simplified? The only way that you can simplify is if there's something you can divide out of every term of the numerator and every term of the denominator. Other than 1, does no good to divide out 1. Other than 1, there's nothing you can divide out here. So that is the answer. But your instructions, I didn't write it here on my instructions, but your instructions will probably say something to the effect of indicate if there is a domain restriction. Is there a value, an x value, a number for x that I cannot use? I didn't bother with any of the other problems talking about that. What's unique about this one that would force me to think about my domain? There is an x value that I can't use. X cannot equal 1/3. That is my domain restriction, but why is that? I need to indicate that x can't be that. What would happen if x was 1/3? If you plugged in 1/3, what do you notice? You would have a denominator of 0, wouldn't you? If you plug it into the denominator, 3 times 1/3 is 1, minus 1 gives us 0. Are you allowed to divide by 0? No, that's undefined. So if we ever have a fraction, we need to think about that scenario. So what I would have done, what I did, is I thought about the denominator, and I know that it cannot equal 0. So I was thinking about that 3x minus 1 can't equal 0. And if I solve that, to get x by itself, I'd add 1, and I'd see that, okay, 3x cannot equal positive 1, and then divide by 3, and then I see that, oh, x by itself cannot equal 1/3. So that's why I had to indicate that as a domain restriction. It was an x value. Remember, domain is x values. What x values are possible? Well, I couldn't use that x value because it gave me a denominator of 0. Not allowed. So I had to restrict the domain. Every other x value is fine. You can use, but that x value you can't. So those are the add, subtract, multiply, and divide. Those are things we've done before. The notation was a little different, and we did have to think about the domain restriction on that division problem. But otherwise, that's not really something that's new. It's the composition of functions that's new. That's what we need to talk about. So let's switch gears. And before we actually get into the composition function, let's start with 2 new functions. I'm going to switch colors also. Let's let f of x equal negative 3x. And let's let g of x equal 5x minus 6. I'm going to ask a question that isn't yet doing the composition of functions, but it's going to be helpful when I get to the composition of functions. So let's go ahead and find, actually not f, I meant to say g. Let me go back. Not of x either. X of 2. Or sorry, g of 2. Let's find out what g of 2 is. When I say find g of 2, what do? You plug it in. What do you plug in? The 2 in place of the x. Okay. So you look at the g tells you which function to look at. The problem said 5 times x, but I'm using that x kind of as a placeholder. It said 5x minus 6, but I'm not going to plug x in there. I'm plugging in 2. The number in the parentheses is what I substitute in. So it means 5 times 2 minus 6, right? So we get 10 minus 6 gives us 4. Okay, so that's something we've done before. That's not new. That's just using function notation. But here's what a composition of functions looks like. F of, and then instead of putting something in there, I put another function in there. G of. So plugging a function into a function. F of G of 2. So before I can worry about the F, I have to think about what I'm plugging in. I have to think about G of 2, and I would have to identify what G of 2 is. Isn't that what I just found though? Yes. So I know that G of 2 is 4, so I just did that problem. So that means I'm doing F of 4. I plugged 2 into the G to get my answer. And so then I plug 4 into the F. So the F function says negative 3 times x, but I'm not using x. I have to plug in 4. Negative 3 times 4 is negative 12. That would be the answer. Now, there is a different notation that means the same thing. I want you to be familiar with both. Our textbook uses both, so we need to identify both. That's the notation I prefer. But here's what you also might see. F of, but they use a new operation symbol. It looks like fog of x, but that's not an O in the middle. It is a little bit smaller, and it's up a little higher. It's kind of like our multiplication dot, except it's open. That means F of G, and the whole thing of x. So that's the same thing as what I just, well, except, sorry, I put in an x there. I should have in the actual problem, I didn't use x, I used a 2. So those notations mean the same thing. So let's switch the order and see if we actually get the same thing. That'll be an interesting question. Plug it in 2 again. G of F of 2. Also the same thing as G of F of 2. They mean the same thing. You don't have to write it both ways, but you'll see it in each of those ways. So it's worth recognizing. So what do I have to identify first? I have to find out what F of 2 is. I leave that G alone initially. So we'll come back to the G, but we need to find out what F of 2 is. So F tells me which function to look at. That's the negative 3x, but instead of x, I have to plug in 2. So right here in this parenthesis, negative 3 times 2, that's what F of 2 is. And negative 3 times 2 is negative 6. So I still have this G. I haven't done anything with that G. It's still out front. And I had plugged 2 in for F to get an answer of negative 6. And now I have to take that negative 6 and plug it into the G. So G says 5 times x, but replace the x. The function said 5x minus 6. So now I get negative 30 minus 6, which is negative 36. Sometimes you'll be asked not to plug in a number, but to leave your answer in terms of x. So here's one where I'm not plugging in a number. If I'm not plugging in a number, I'm not going to get a number out as an answer. I'll have something in terms of x. So the first letter, or the letter on the outside, is the F. Leave that alone. For now, we'll come back to that. And what do I plug into that? I plug into that g of x. But I know what g of x is. That's 5x minus 6. There is no simplifying to do on that. That is simplified. So now I have to plug 5x minus 6 into the f function. So the f function was negative 3x, negative 3 times x, over here. So instead of x, I put parentheses, and I have to plug into that. We'll switch colors here. This 5x minus 6 has to get plugged into that. So negative 3 times that gives us our answer. Let's do one more. So we're going to do g of x. I don't have to use two different functions. I could plug a function into itself. So that's what I'm going to do here. So the first letter stays out front. I have to start with g of x. What is g of x? 5x minus 6. No simplifying to do on that, so I'd have to plug 5x minus 6 into 5x minus 6. So the g function says 5 times x, but I'll leave a parenthesis there instead. 5x minus 6 comes from here, but I replace the x with a parenthesis right here. 5 times something, minus 6. And then I have to plug this in. 5x minus 6. 25x minus 30 minus 6 simplifies to 25 minus 36. Sorry, it's 25x. Forgot the x there. 25x minus 36. That's composition of functions. That concludes the notes for today.